Have you ever looked up at the vast, beautiful sky and wondered, why is it blue? You might have heard a simple answer, like, the sky reflects the ocean. But that's not quite right. The real reason is a fascinating journey into the world of light, air, and a brilliant scientific phenomenon called Rayleigh scattering. Stick around, and by the end of this video, you won't just know what makes the sky blue, you'll understand how it happens. To understand the sky's color, we first need to understand the nature of sunlight. What we see as white light from the sun is actually a mixture of all the colors of the rainbow. Think of it like a team of runners, all starting a race at the same time. Each color is a different runner. We can visualize these colors as waves, each with its own specific wavelength. Red light has a long, stretched-out wavelength, like a runner taking long, slow strides. On the other end of the spectrum, blue and violet light have very short, choppy wavelengths, like runners taking quick, tiny steps. This difference in wavelength is the key to everything. Now, let's introduce the second player in this story, Earth's atmosphere. Our planet is wrapped in a thick blanket of gases, mostly nitrogen and oxygen. These gas molecules are incredibly tiny, much smaller than the wavelengths of visible light. When sunlight enters the atmosphere, it's like our team of runners hitting a field full of scattered obstacles. The light waves don't just travel in a straight line, they start colliding with these gas molecules. And this is where the magic happens. The way light interacts with these tiny gas molecules is described by a principle called Rayleigh scattering, named after the 19th century physicist Lord Rayleigh. He discovered that when light hits a particle that is much smaller than its wavelength, the light gets scattered in all directions. But here's the crucial part. Not all colors are scattered equally. Rayleigh scattering affects shorter wavelengths much more strongly than longer ones. Remember our runners. The long wavelength red light, with its long strides, can mostly step over the tiny obstacles, the gas molecules, and continue on its path with little disruption. But the short wavelength blue light, with its quick, choppy steps, is constantly bumping into these molecules and getting knocked off course, scattering in every direction. In fact, blue light is scattered about 16 times more effectively than red light. So, when you look up at the sky on a clear day, what you're seeing isn't the light coming directly from the sun. Instead, you're seeing all of this scattered blue light. It's coming at you from every direction, bouncing off countless gas molecules all across the atmosphere. This scattered blue light fills the entire sky, creating the beautiful blue dome we see above us. The direct sunlight that isn't scattered as much, the reds, oranges, and yellows, continues mostly straight on its path, which is why the sun itself appears yellowish-white. You might be thinking, wait a minute. If shorter wavelengths scatter more, and violet has an even shorter wavelength than blue, why isn't the sky violet? That is an excellent question, and it has a two-part answer. First, the sun doesn't emit all colors with equal intensity. It actually gives off more blue light than violet light. So, there's simply more blue light available in the atmosphere to be scattered in the first place. The second part of the answer lies within our own biology, the way our eyes perceive color. Our eyes have specialized cells called cones that are sensitive to red, green, and blue light. When the scattered light from the sky reaches our eyes, it's a mix of blue and some violet. However, our blue-sensitive cones are stimulated more strongly by this mix, and our brains interpret this combined signal as the familiar color we call sky blue. So, in a way, the sky is blue, not only because of physics, but also because of how our own eyes and brain are wired to see the world. This same principle of Rayleigh scattering also explains the breathtaking colors of sunrises and sunsets. As the sun gets lower in the sky, its light has to travel through much more of the atmosphere to reach our eyes. Think of it as a much longer, more crowded obstacle course for our runners. During this long journey, almost all of the blue and violet light is scattered away from our direct line of sight. It's bounced off in so many other directions that very little of it makes it straight to us. What's left? The longer wavelengths, the reds, oranges, and yellows. These colors, which were less affected by scattering, are the ones that finally complete the long journey through the dense, low-altitude atmosphere to reach our eyes. This is why the sun and the clouds around it can glow with such intense and fiery colors during sunrise and sunset. The more particles in the air, like dust or pollution, the more scattering occurs, which can lead to even more dramatic and vibrant red sunsets. So, let's recap the how. Sunlight, a mix of all colors, enters Earth's atmosphere. The tiny gas molecules in the air scatter the light. Because of a principle called Rayleigh scattering, short wavelength blue light is scattered far more effectively than long wavelength red light. This scattered blue light fills the sky, coming at our eyes from all directions, making the sky appear blue. During sunrise and sunset, the light travels through more atmosphere, scattering away the blues and leaving the beautiful reds and oranges for us to see. The next time you gaze at the sky, you'll have a deeper appreciation for the intricate dance between starlight and air that paints our world every single day. It's not just a color, it's a beautiful demonstration of physics happening on a planetary scale. Thanks for joining us here at HowLab, where we learn how, not just what. If you found this explanation helpful, please give this video a thumbs up and subscribe for more deep dives into the science behind our world. See you next time.